Chemistry, the Central Science, Chapter 10, Gases, Lesson 1. So let's just review what some typical physical properties are of gases. So in terms of volume, a gas is going to take on the volume of the container as well as the shape of the container that it's in. Gases are highly compressible because the distance between gas molecules is so large. So that means that you can fit them into a smaller space by decreasing the volume, which then would increase the pressure. So mixtures of gases will always be homogeneous. So you have a solution, like the air that we breathe is a solution where nitrogen is the solvent and oxygen is the main solute. And the densities of gases tend to be very small compared to solids and liquids. So pressure is something that is going to affect a gas, or it's a property of a gas that we can study, which does not affect liquids and solids. So pressure is defined by a force over a given area. Force in terms of physics, right, is mass times acceleration, where we measure that in a Newton, which is a kilogram meter per second squared. So some typical units of pressure that we're going to use, well, a Pascal is a Newton per meter squared. And at 1 atmosphere is the same as 760 millimeters of mercury, which is the same as 760 torr, which is after torricelli. And then 1 atmosphere is also equal to 101,325 pascals, or 101.325 kilopascals. So on the right-hand side here, this picture is showing a barometer. So we have a pool of mercury, and then we have a tube that is inverted. So the density of mercury is 13.6 grams per milliliter, and it's not going to evaporate readily, which makes it a really good liquid to use for measuring pressure. So effectively what happens is, as the atmospheric pressure increases, the height to which the mercury will go up into the tube will also increase. Therefore, it's proportional. So the pressure is proportional to a length or a distance within the tube. So over here we see that this is 76 centimeters of mercury, which is the same thing as 760 millimeters of mercury. So this is a barometer, and this is what we use to measure pressures. So we can also use a manometer to measure pressures of specific gases. So in a closed tube manometer, right, so it's this U-shaped device, we have the ability to, we have the gas in this volumetric end of the flask. And as the gas is released into the tube, we can see that whatever the pressure of the gas is will then push the mercury into the adjacent tube. And once again, we can simply measure the difference in the heights between the two tubes, and that would tell us the pressure of the gas. So it's a closed tube, and we have it in a vacuum, so nothing else is affecting the pressure other than whatever the pressure of the gas is. Now, if we have an open tube, so that means we're open to atmospheric pressure. We have this similar apparatus set up. However, we have atmospheric pressure now pushing down on the mercury on the right-hand side of the tube, and the gas is having its own pressure, which is trying to push against atmospheric pressure. So once again, we measure the height difference, but because this is open to the atmosphere, we also have to take into account what is the pressure of the atmosphere. So now we can calculate the pressure of the gas by looking at the difference in the height between the two tubes and then adding atmospheric pressure to it. So we're going to take a look at 3 major gas laws. So the first one deals with, or is called Boyle's law. So if we look at our cylinders here, in our first set of circumstances, pressure is 1 atmosphere. We see that the volume is 10 liters. And we notice that we are not changing our temperature. So we're keeping the temperature constant as well as keeping the number of moles of gas constant. So from piston 1 to piston 2, we can see that we've doubled the pressure. And in doing so, we've halved the volume. And then once again, if we go from piston 2 to piston 3, we can see that once again, we've doubled the pressure. Therefore, we've halved the volume. Or if we look at system 1 and system 3, we've quadrupled the pressure, so we have 1/4 of the volume. So if we want to plot a straight line, which gives us great information, a linear plot, we're going to plot pressure versus the inverse of volume. So that gives us a straight line. So it tells us that pressure and volume are inversely related. And we can only measure this if we have a constant temperature and a constant amount of gas. So we then have an equation that says the pressure times the volume equals some constant. And we can set up proportionalities, which say our initial set of conditions of pressure and volume equal a final set of conditions of pressure and volume. So if the pressure increases, the volume would decrease. If the pressure decreases, the volume would increase. So Charles studied the relationship between volume and temperature. Now we notice here that our temperature has to be measured in Kelvin. This is always true when we're studying gases. So from system 1 to system 2, we can see here that we're not changing the pressure, well, in any of these circumstances. So from 1 to 2, we look at doubling the temperature in Kelvin results in doubling the volume. If we look from system 2 to system 3, we've once again doubled the temperature, so we double the volume. Or from 1 to 3, we look at quadrupling the temperature leads to a quadruple change in the volume. So these volume and temperature are directly related. So the hotter a gas is, the more it's going to expand, the more volume it's going to take up. So in studying different gases, we look here at different pressures. What is the volume temperature relationship? Well, no matter what pressure the gas was studied at, every single line would extrapolate back to what we call absolute zero in terms of Kelvin, or negative 273.15 degrees Celsius. So this is how the Kelvin temperature scale was determined, because Kelvin is not dependent on the physical properties of a desired liquid, such as water. So we studied different gases, regardless of what the gas was, regardless of what the pressure was. Volume temperature proportionality would always lead back to absolute zero. So we have an equation now which says the volume equals a constant times temperature, or if we put that, volume over temperature equals a constant. And our initial set of conditions then, volume 1 over temperature 1 equals volume 2 over temperature 2. So because these are directly proportional, an increase in the volume would result in an increase of the temperature, or a decrease in the volume would result in a decrease of temperature. The most important thing when using this equation is making sure that your temperatures are in Kelvin. If you do not convert to Kelvin, you will not get the right answer. And when we're looking at Charles' law, we keep in mind that we're not changing the pressure and we're not changing the amount of gas. The last law that we're going to look at is Avogadro's law, which we know he studied moles. So if I look at this equation here, this reaction, so 3 moles of hydrogen react with 1 mole of nitrogen to produce 2 moles of ammonia. Moles and volumes are directly proportional to each other, so we can look at this as well as saying we have 3 volumes of hydrogen plus 1 volume of nitrogen to yield 2 volumes of ammonia. And when we are studying volume and moles, we have to keep constant temperature and constant pressure, because we looked at these other 2 laws which say if we alter one of these, it's also going to affect the volume. So volume is directly proportional to a number of moles. Volume equals a constant times n, or V over n equals a constant, such that an initial volume divided by an initial set of moles equals a final volume divided by a final set of moles. So once again, if we increase the number of moles, we would increase the volume. If we decrease the number of moles, we would decrease the volume.